Okay, so now that we've got a model and we've backtested it during a time period outside of the data range, and then we simulated how one of these portfolios would perform given a year time frame, we can look closer at the overall program and just look at the finer details. So just looking at the main function, first it just gets the portfolio parameters, and that refers to the securities listed as well as the range of dates. And then we just process that data, and that just means getting the all the different prices from YahooFinance. And this is done in the df helper file that refers to data frames, and that's just from pandas. That's an element within pandas. And you're also, by the way, going to want to import the YahooFinance API. So we went with daily returns, as I said. So this is going to get the closing price of all the inputted securities. And then all of this code right here, that just goes towards making sure that all of these securities are listed. And remember, we found that Google was not listed beginning in 2000 and actually did not IPO until 2004. So that's what that does. And once we have all of that data, we've got all the standard deviations, mean returns, covariance matrix, and then an updated list of what we want to include in our analysis. We're then going to look for this point right here. This is called the global minimum variance. So that is done in the matrix manipulation file, and that just uses NumPy. So this is the function right here that does it. Okay, so now let's look at the equations that this function uses. All right, so this is the variance of a portfolio with three securities, A, B, and C. So we want to minimize that variance such that our allocations into A, B, and C sum to 1, or in other words, that we're fully invested. So M just represents the weights. Okay. So another way to think about this is that this is the constraint function, and this is the objective function. So we know that if we take the gradient of the objective function and the gradient of the constraint, they've got to be parallel. So there is going to be some scalar value that relates the two. So now to make things easier, we're going to create this Lagrangian function right here such that when we take its gradient, we end up with the desired conditions. So that's going to create a system of linear equations that we can put in matrix form so that the computer can easily work with it. So notice, most importantly, when we take the partial derivatives with respect to these weights of this term right here, what we're getting is just the Lagrange multiplier itself. And so all we have to do is take the partial derivatives of this and pretty much set it equal to the multiplier itself. And that's what you see here. If you do matrix multiplication, you'll see MA times this term, MB times that term, MC times this term, plus the Lagrange multiplier has to equal to 0. And again, we don't care exactly what it is, so it can be negative of that, positive of the multiplier. We don't care about the actual value. So that's why sometimes for Lagrange multipliers, you'll see a negative here or a positive here. It doesn't really matter unless you care about the value. So the other lines are just the same thing. And then the last line is just simply that MA plus MB plus MC have to equal to 1. So that's what you'll see when you look through this function. You'll just see we're creating those rows of zeros and ones and just twice the covariance matrix. And then we just invert that matrix and solve for the weights. And because we only want the weights, we're going to index out that Lagrange multiplier. So now that we have the weights, those are given right here, of the minimum variance portfolio, and we can then use those to calculate the standard deviation and the daily return. So we've got this point right here, and now the approach that I'm going to take to build out the efficient frontier is to just get a range of returns above and below this point, and to just calculate the minimum variance for each of those returns. So that just builds out the efficient frontier. So that's what you're going to see in this function right here, efficient frontier. It's just going to take in a list of mean returns, a covariance matrix, and a list of desired returns. So that's that range I was talking about. And it's then going to, for each of those, for each R and RS, it's going to calculate the minimum variance portfolio, and then we can get a list of standard deviations and weights based on that. This function is calc Mean-Variance Portfolio, and as I said, that's just going to take your expected returns, your covariance matrix, and then your desired returns. So that's for each of the R and RS. This is one of the R's. And now we're going to do some matrix algebra. So again, we're going to want to minimize the variance, which can be represented by the weights transposed times the covariance matrix times the weights. But this time we've got two constraints. The first constraint is we have a desired return. So we want the weights transposed multiplied by the mean returns to equal that desired portfolio return. And also we have the same constraint as before, namely that we're fully invested, or the weights transposed should sum to 1. So again, we're going to represent this with a Lagrangian equation. And so we just put all the terms together such that when we take its gradient, we get our conditions back. So here's the system of linear equations, which is just the gradients as mentioned before in matrix format so the computer can use it. And this is just twice the covariance matrix. And again, you can see, so lambda 2, that's the Lagrange multiplier for ensuring that the weights sum to 1, that we're fully invested. And again, that's just when you take the gradient, you end up just getting lambda 2 by itself, and then lambda 1 multiplied by the weights vector. So twice the covariance matrix should equal to negative lambda 1 times that and negative lambda 2 times that, because we've just got a 0 here. And you can, again, we don't care about the actual value here, so you can take those as negative, positive, whatever you want. And then the second two lines, those just give us our constraints, namely the weights times the returns should equal to our desired return, and then the we're just summing all the weights to 1. That should equal to 1. So now you see how we got this efficient frontier right here. We just did that for every single point. You can make the range as big as you want, but I found that this is about reasonable. You don't want to have a standard deviation that's too high. That's really the limiting part of this. You need to, there's a certain measure of risk that you don't want to go above. So looking at the calc minimum variance portfolio function that we were just talking about, if you go through this, you'll see again, I'm just constructing that matrix that I put up for you. And then at the end, we use, again, NumPy's linear algebra solver. And then because now we have two constraints, we're going to be taking the weights and excluding the last two elements of that list, which are those Lagrange multipliers. So now we can look at the backtesting, and this is what the first form of backtesting is what I jokingly call real test, because we're actually we're taking that efficient frontier and we're going to apply it to a set of data outside of what the model uses, so that we can see how well this model is able to sort of predict the future. How well does the model perform outside of the original date? So what we're doing is we're putting in two new start and end dates. We're going to interact with the user, get those new start and end dates, use the same tickers, and we're going to process that data, and then we can get a real return and a real standard deviation of how that efficient frontier does during a different time period. And so when you look at the graph, as I said before, you'll see that it actually flipped. The efficient frontier in this instance did not do that great of a job, really, of predicting the returns and standard deviations. I mean, it wasn't bad, but so 1 refers to down here and 10 refers to up here, but you can see we've got 1 all the way up here and 10 all the way down here. So yeah, this performed as I said in the first video, Microsoft performed a lot better than expected during a different time period. We originally thought that Microsoft, during this time period here, Microsoft was sort of the bottom of this group, whereas during the time period that we're using for the real test, we find that Microsoft really outperformed expectations. So that's why, as I said before, we get this reversal. And so that's all there is to this component of backtesting. We just build out that frontier, really using the same methods as before. So now let's look at Monte Carlo. And I used object-oriented programming for this. Just thought it would be easier to create a class based on how I've used it before. And really all you need to look at for this one, here's the line right here. This will, because this is actually might be a little controversial. There's better ways possibly to get to simulate. All I did here is get a random z-score based on and I get a random z-scored using NumPy, and then I multiply that by the standard deviation, and then I just add that to the return. And so that's what we're using to simulate the return. And then we can use that to simulate values, and then ultimately plot those values.